My name is Campbell Mutert, and this is my video lab 2 for the lines of charge revisited. So the purpose of this lab was to produce a computational model of two charged tapes exerting an electric force on each other, and estimate the amount of charge necessary to float one above the other, distributing the charge evenly across the length of the tape, which is different than lab 1, which used a point charge, and then compare those results. The results for this lab was that the magnitude of the charge of the tape was 1.95 times 10 to the negative 8th coulombs, which is more than twice the value calculated in lab 1. Important physics concepts for this experiment are the momentum principle that says if there's no change in momentum, then the net force is 0. Coulomb's law says that the electric field is K times Q1, Q2 over the distance between the two particles squared over r hat, and the gravitational force is mg in the negative y hat direction. And since the tape is floating, F net does equal 0, and the force of gravity is then equal to the electric force. We can use that to set the electric force equal to Q times the electric force of a rod, which is KQ over R times the square root of R squared plus L over 2 squared. And then set that equal to the gravitational force and solve for Q, which I found to be 1.953 times 10 to the negative 8th. The assumptions for this lab were that the strip of tape is a line of charges, and that each strip had approximately equal amounts of charge with even distributions, and that air resistance and loss of charge is negligible. In this experiment, the system is tape B and the surroundings tape A and the Earth. The length of the tape was 0.185 meters, the width was 0.02 meters, its mass was 1.85 times e to the negative 4th kilograms, and the tape was stationary when the distance was 0.02 meters. The constant K is 9 times 10 to the 9th. The gravitational constant is 9.81, and there's a picture of the model. So for the code, I input the physical constants K and G, the mass, the original charge just for later comparison, the Q that we calculated on the last slide, the length and the distance, and then the electric field. I used my work from lab 0, which was that Q is the charge, R is the observation location minus where the charged particle is, the magnitude, and r hat is the direction, and then the electric field is KQ over r squared, r hat. Here is the section of code that creates the actual line of charge. Both the top and bottom tapes start at 0 in the x direction, and then the top tape starts at a distance in the y direction, and both the tapes are the length long with mass m, charge q with 100 observations, and the scale is set for the arrows, and then the electric force and the gravitational force are set equal to each other, and then for each charge in the tape, they're calculated, and that's done for both the top and bottom, and then they're scaled. This section of code was just creating the arrows and then scaling them and printing out the results. So the results were that the electric force was 1.65212 times 10 to the negative 3rd newtons. The gravitational force was 1.81485 e to the negative 3rd newtons, and the magnitude of charge on one piece of tape is 1.95365 times 10 to the negative 8th coulombs. So the computed value was really close to the actual value, but a little bit less, and the sources of error were that I estimated the separation distance and the weight. There could have been loss of charge with handling, or unequal charges of the tapes, or other forces from the surroundings. For the what if question, the line charges result more closely with the actual Q than the point charges from part 1. As you can see, it's almost twice as big. So 1.95 times 10 to the negative 8ths compared to 8.98 times 10 to the negative 9ths. And then I used trial and error to find the actual Q. which was 2.05 times 10 to the negative 8th, and lab 2 was closer. And the estimates vary because the methods to calculate the charge of the point or line charge differ, with the line charge probably being more accurate because in real life charges distribute over the surface, and using more segments gets you closer to the true mean.